Okay, for this system, we have some material. We have a cross section here. We can see it's insulated, and there is a temperature source out here. All right. And what we want to do is model how, as this material is exposed to this temperature, how it heats up. So suppose this is a high temperature source, then this will heat up. And let's think what will happen. It's insulated, so we'll assume it's perfect insulation, so the heat can't escape anywhere. So this will begin storing heat and storing heat and storing heat. So we have, so if you ask the question, okay, what will the temperature be out here compared to the back? Well, that's obviously as it heats up, the front will have one temperature, and then the back will have another. So how do we want to deal with this? And so we can do that because we know the temperature will not be uniform by dividing to get a model to divide this up into components. For example, so to transport the heat into here, we could have like a resistor and then have a region we model as the capacitor that stores some heat. And then we could have another resistor and then another capacitor. In fact, that's a strategy that's often used. When you get into what would be called finite element model, we take something and we break it up into whole piles of different parts. So you could have, resistor, capacitor, resistor, capacitor, resistor describing the heat moving in, and then some level of heat being stored. And then there's another resistor, another capacitor on going back. We're going to divide this up into two RC regions as so. So the resistor just transports the heat via conduction, and then here's an area where some level of heat is stored, and of course this will have a different temperature here, so there'll be another resistor. And so the idea, what we'd like to model is understand the temperature of this back capacitor as a function of time as heat comes in and winds up getting stored here. All right. So capacitance stores heat with a uniform temperature. Uh, so we have, relative to this capacitor, we have heat coming in from here and heat going out, going to there. So Qn equals 1 on R. Okay, and keep in mind that temperature is like voltage and heat flow is like current. So Ri equals V in the electrical world. So we're just modeling heat, we're just moving the R to the other side. So 1 on R, theta I minus theta 1. And then the heat out would be 1 on R, theta 1 minus theta 2. All right. Then we have the capacitive effect. So so for this capacitor, and we'll let both of them be, because it's all one material, so we'll let them have the same properties. So Q in minus this Q out equals this capacitance, theta 1 dot. So that as it stores heat, this temperature will go up, hence it has a derivative. All right. So we have C theta 1 dot equals Q in minus Q out. So these are the same resistors, so we can just say R1 theta I minus C, and then going out, we would have minus theta 1 plus theta 2. So it's minus Q out. That way we get a minus sign here and a plus sign there when we combine them. And here's our equation. Theta 1 dot, 1 on RC, theta I minus 2 theta 1 plus theta 2. Now, we don't really care about theta 1, so we're going to want to get rid of that in a bit. But let's first deal with what is the equation for this back capacitor. Well, this just has heat coming in, so that'll be 1 on R, theta 1 minus theta 2 coming in is C theta 2 dot. So that's the process of it heating up. Okay, and then we can just solve for theta 2 and we get 1 on RC theta 1 minus theta 2. All right, so I'd like to have a transfer function that takes me from this output or of this piece outside of the device, theta I, and relating it to theta 2. So now we go to Laplace. So we can take this piece right here, bring the RC over, apply Laplace transform, so that becomes S theta 2. And I'll bring the theta 2 to the other side. So that gives me this equation. This becomes that. All right. And then we'll address this one up here. Okay, so when we bring this to the other side, I'll bring the theta 1 to the other side. So I have 2 plus RCS theta 1. I'll bring the theta 2 to the other side, then it becomes negative equals theta I. All right, I don't care about theta 1. I care about theta 2. So if you look here, theta 1 is equal to theta 2 of S, 1 plus SRC. So I can take this piece and stick it down in here. Then I'll have theta 2 as a variable along with my theta I. And that's what we get. All right, form a transfer function. This is the output, that's the input. So we divide this one over to here and all of this mess to this side, and we get that. There is our answer. And this problem is done. Talk to you again soon.